Hi, I'm Ellen, and I'm a PhD student with Rui Ponte Costa and Richard Apps at University of Bristol. And together in my work with Joe Pemberton, we propose a model for how the cerebellum interacts with the neocortex and using ideas from deep learning. And I will show you that corticocerebellar networks are important to support temporal feedback predictions in the brain. But first, we know that the cerebellum has widespread connections with the cerebral cortex. These corticocerebellar interactions play an important role in motor learning and adaptation. However, experimental evidence shows that it is important for processes as well beyond motor control. But the function of these networks is not well understood. And in this project, we're interested in understanding the role that the cerebellum plays when interacting with the neocortex. And to address this question, we build on the notion that the cerebellum and its circuitry systems function as a predictor or an anticipator. And this is well known in the sensory motor domain, as we can see here on the schematic on the right. And this schematic illustrates that the corticosensory feedback, for example, when moving your arm or reaching somewhere, that these corticosensory feedback process operates slowly, much too slowly for us to generate behavior in real time. So based on this idea of the cerebellum being an anticipator, we introduce a deep learning framework of corticocerebellar function in which the cerebellum decouples activity in the brain. And so how does this work exactly? Imagine you're doing a delayed target reaching task in which you get given a certain stimulus, you have to move to a target after a certain delay, as you can see here. But let's say that we model this task and that we approximate, for example, the motor cortex by a recurrent neural network. And thus comparing the network output with the target at the end of the sequence, this will generate learning signals or feedback signals that can be used to update the network. And based on cerebellar function and anatomy, we can introduce a separate network with which the main network communicates, and the neocortex can send a copy of the motor command activity, which is then used by the cerebellum to make predictions about this sensory feedback, if you will, of this command. And so thereby passing this more slow cortical feedback. And in this framework, we refer to it as corticocerebellar decoupled neural interfaces, as the cerebellum decouples the feedback activity. And in our model, we see that having this extra component, that this reduces the need for strong memory requirements in cortical networks, and thus supports temporal credit assignment. And we know that temporal credit assignment is linked to the ability of neural networks to link teaching signals to the input signals that we get in the world. And so we validate our model in classical sensory motor tasks. Again, here we use a target reaching task, and we can capture qualitative results of cerebellar patients, being that they move to the targets much more slowly, as you can see here on the top for 3 models, a model without the cerebellum, and then our 2 variants with our cerebellar components. And also we see that the networks learn much faster. And this we also find that the speed up depends on input teacher delay, like with maximum speed up around like medium to longer delays, except for when the delays get too long. And this is in line with more recent experimental evidence. And we also validate our model in more complex sensory motor and pattern generation tasks. And therefore we use the standards machine learning sequential MNIST data sets. And so here you can see 2 variants of the task. On the right, a drawing or a reaching version, given a more complex set of visual inputs. And here on the bottom, the 2 respective learning curves of the models on this task. And finally, to make the link with studying the cerebellum in more cognitive behaviors, we model the cerebellum in a language processing task. And studies have shown that the cerebellum is necessary for language prediction, but also capturing context in language. And here we use a caption generation task in which the network learns to generate a caption given a certain image, as you can see here on the top. And we see that our cerebellar models, as you can see here, generate overall much better captions when comparing our 3 different models to a golden standard caption, here shown in black. And this is also the fact that our cerebellar models improved performance is also reflected in the learning curves of the model. So to conclude, we propose a deep learning model of corticocerebellar function, and we show that some of our results are qualitatively consistent with some cerebellar deficits in motor and non-motor learning. And we know that the cerebellum is anatomically well positioned to provide temporal feedback to the neocortex, and that this supports temporal credit assignment in the brain. And the cerebellum becomes increasingly important with task difficulty due to the inability of cortical networks to maintain information for long periods. And this is in line with some recent experimental results.